Good evening, sir.
Yes, good evening. Yes, let me start. Briefly introduce yourself.
So my name is Avantika. I belong to Hisar and I have completed my BSc M.Sc dual degree course in chemistry honors from Guru Jambheshwar University of Science and Technology, Hisar.
Yes, good. Last day we have discussed. You tell us we are starting from. Yes, today topic is John Taylor distortion. Yes.
Yes, sir.
Yes. Let me start on board. John Taylor distortion. What the basic principle of John Taylor distortions? Explain.
Sir, dis- John Taylor distortion. Any system in universe which is non-linear, if it is in electronically degenerate state, then it wants to remove its degeneracy, and in the process of removing its degeneracy it lowers its symmetry to gain the stability, and in this process while losing its symmetry some distortions occur which are known as John Taylor distortion. And Taylor distortion in occurs in if the EG orbital or T2G orbital is unsymmetrically filled.
Yes. How many
And
types of John Taylor distortion?
Sir, it can be Z out or Z in distortion, or triaxial distortion also occur in triclinic system. And Z out distortion mostly occur if EG orbital is unsymmetrically filled, and Z in distortion mostly occur if T2G orbital is unsymmetrically filled. They are also if EG orbital is unsymmetrically filled, mostly there is static distortions, but there are also some exceptions where bond length changes doesn't occur. There dynamic distortion occur.
Yes, good. Explain
Thank
on
you.
board. Yes. Whiteboard.
So, for example, if we have taken
First, yes. First note on topic name. John Taylor distortion. N is start.
John Taylor distortion,
ये वर्टिकल हो रहा है हॉरिजॉन्टल कीजिए इसको.
like this.
Yes, right. Yes, explain on board example one by
Yes.
one. Which example show in John Taylor distortion and why?
So, for example, there is a electron in a first of all, sir, it John Taylor distortion occurs to re- remove its electronic degeneracy. So, in if we take the case of EG orbital, there are two possibilities that if we fill one electron, then one electron can be in dx square minus y square, or it can be in dz square. So if one electron will be, suppose if one electron will be in dx square minus y square, then we if draw the orbitals in dx square minus y square.
Yes.
then here electron is present, and if ligand approaches towards the axial orbitals, then here will be more repulsion occur, and due to this the energy of this x and y axis containing orbitals will be raised, and in dz square
Yes.
if the ligand is approaching in this direction, first of all we can also say this as if we have taken the dxy orbitals which are in between the axis, then here if the electron is in this dz square orbital, and s orbital is here, so the electron if the ligand is approaching towards this z direction, then here more repulsion will be occurring as compared to this x and y direction. Here one more case is possible.
Yes.
In this we can also take it as a z effective, because if the electron is present in dx square minus y square orbital, then here will be less z effective because of the shielding effect. So in this dx square minus y square, due to less z effective, its bond length will decrease as compared to the z axis. And so in the case of dx square minus y square, z in case occurs, and if we have taken dz square orbital, if the electron is present in dz square orbital, then the shielding effect occur in this, and the z effective will be lowered. So here in case of dz square orbital, z out case will occur. We can take the example of John Taylor distortion as in case of D9. We can take example of copper H2O 6 2 positive. Here Cu2 positive has D9 configuration, and if we fill these D9 configuration as here as case of octahedral complex, then here T2G orbital and EG orbital. So if we fill this, So it comes as configuration as T2G6 and EG3. So the case of here is the case of EG unsymmetrical. So here Z out JTD will occur, and in Z out JTD, if we split further these orbitals, so in Z out the energy of dz square orbital will be decreased, and dx square minus y square is, and in here is dxz and dyz orbitals, and here it is dxy orbital. So this is the JT12. So here the gap between dx square minus y square is can be called as delta 1, and the gap between dxy and dxz and dyz is delta 2. The delta 1 is greater than delta 2. So this is the diagram of JTD in case of D9 configuration in the complex of CuH2O6 2 positive. And further there are in case of we can take 4 examples here. If we have taken CuH2O6 2 positive and one is K2PB CuNO2 6, so here in both cases of copper is in +2 oxidation state, and we have taken two more examples, that is TiCl6 3 minus and TiH2O6
Yes.
3 positive. In both of these, Ti is in +3 oxidation state. We have now discussed the case of CuH2O6 2 positive with diagram. So here it have come out that it has Z out JTD. But if we take the case of CuNO2 2 positive, or we have observed that all bond lengths are equal. But here in case of Z out, the bond length along the Z axis is very much greater than the bond length along the X and Y axis. So the the consequence of strong JTD is that the bond length changes. But here in Cu2 positive with NO26, we observed that here JTD occurs, but all the bond lengths are equal. So here in both these cases, electronic degeneracy is present. So the difference is that here in CuH2O6 2 positive, static JTD, and in K2PB CuNO26 there is dynamic JTD.
Yes.
And if we have taken the case of TiCl63 minus and TiH2O63 positive, here also in case of Ti3 positive, there occurs Z in configuration, Z in JTD, because it is T2G unsymmetrically filled. And in case of TiH2O63 positive, distortions occur. Here also Z in JTD occurs because it is also T2G unsymmetrically filled. But in case of TiCl6, we have observed that the bond length along X and Y axis is more as compared to the Z axis. And in TiH263 positive, all bond lengths are equal. So here the reason can be Berry pseudo rotation, or here the reason can be Berry pseudo rotation. And if we have observed it on same temperature,
Yes.
there are few more examples of dynamic JTD. If along with CuH262 positive, TiH2 instead of TiH263 positive, if we have taken iron, then here also dynamic JTD will occur and we will observe all the bond lengths are equal.
Yes. Good. Any limitation of joint tailor distortion?
So, with the help of John Taylor distortion, there are some consequences of John Taylor distortion like bond length, changes in bond length, and thermodynamic stability and kinetic stability. But John Taylor distortion, some cases are there where John Taylor distortion occurs, but we can't see it because it is dynamic in nature. If in those complexes pseudo rotation or Berry pseudo rotation occurs, so we can't explain that.
Yes. Yes, carry on, carry on.
And in if the bond length is not changing, then we can say that John Taylor distortion is present or not.
Yes, yes, carry on.
So, and another consequence of John Taylor distortion is thermodynamic stability and
Yes, yes.
because of John Taylor distortion, thermodynamic stability is also increased and kinetic reactivity is also increased.
Yes, good. What is spinels? Next topic, not on board. What is spinel and how many types of spinel? What the basic principle of spinels in coordination chemistry?
So spinels are mixed oxides Ab2O4. There are two types of spinels, normal spinels and inverse spinels. In normal spinels, one metal is in +2 oxidation state, which is present in tetrahedral void, and another metal is in +3 oxidation state, which is present in octahedral void, and there is also oxide ion which is present in FCC. Whereas in inverse spinel, one metal is present in +2 oxidation state in octahedral void, and one which is in 3 positive oxidation state is present in tetrahedral void, and another which is in +3 oxidation state is present in octahedral void, and oxide ion is present in FCC.
Yes.
In spinels Ab2O4, A can be equal to B or A cannot be equal to B. In normal spinels, the metal which is in +2 oxidation state, that is A+2, it is generally sp3 hybridized, and which have +3 oxidation state is generally D2sp3 or sp3d2 hybridized. And in case of inverse spinel,
Yes.
the metal which is in A+2 oxidation state, it is D2sp3 or sp3d2 hybridized, and which is in B+3 oxidation state, it is generally sp3 hybridized, and another is sp3d2 or D2sp3 hybridized.
Yes.
So here we have observed that the B+3 ion is present in tetrahedral void. So there is a parameter called as spinel parameter, which is denoted by lambda. We can find out that spinel parameter by finding the number of B+3 ions which are present in tetrahedral void upon total number of B+3 ions. So generally the value of lambda lies between 0 and 0.5. If the value of lambda is 0, then we can say it is normal spinel, and if it is 0.5, then it is inverse spinel, and if it is in between, it can be called as partial. We can also calculate percentage inverse character in a spinal.
Yes.
The percentage inverse character in a spinal can be calculated by the lambda which the spinal have. Suppose AB2O for any spinal we have taken whose lambda is between 0 and 0.5. So the percentage ionic character will be calculated by the value of lambda divided by the lambda maximum, and lambda maximum is 0.5. So here lambda divided by 0.5 into 100, here comes to value is equal to 200 lambda. So if we have to find percentage inverse character in case of any spinal, then we can use this formula, that is 200 lambda.
Yes, good. If any limitation of spinals in coordination chemistry?
Limitation. Sir, so there are some complexes if we find their normal and inverse character, but in actual their normal and inverse character is opposite. For example, if in case of iron plus 3, mostly the answer we have calculated normal or inverse, it
Yes, good. Next, according to ligand field theory, MO diagram for sigma bonding in tetrahedral, MO diagram for sigma bonding in octahedral, MO diagram for bonding in square planar complex. Do you know?
sir, in a ligand field theory, uh, firstly the ligands will combine to form ligand group orbitals. In a normal molecular orbital theory, the molecular orbitals will combine to form so molecular orbitals will combine to form atomic orbitals will combine to form molecular orbitals. And in ligand field theory, if we have to form MO diagrams in coordination chemistry, then we have to do first grouping of ligands. If we take case of octahedral complex, then there are 6 ligands present, and these 6 ligands will the atomic orbitals of these 6 ligands will combine and form a ligand group orbital, and then this ligand group orbital will combine with the atomic orbital of metal to form a molecular orbital complex of Ml6. We can take, we can see this as,
Yes.
if we have taken case of Ml6, then here are 6 ligands present. And these, the atomic orbitals of all these will combine to form 6 ligand orbitals, and it will combine with metal. Here it is ligand group orbital, and here the atomic orbital of metal. So here we will get Ml6 as the complex. We can, for forming MO diagrams of octahedral complexes with sigma donor ligands, then if we have to take ligand, the one atomic orbital of ligand with sigma donor ligands, then we can draw so here 6 ligands are present. These 4 ligands are in X and Y direction, and this is in Z direction. So to represent, we can see this as the wave function in this direction is as sigma x, and here this is sigma minus x, just to denote the opposite direction. Here the wave function is sigma y, and here is the wave function is sigma minus y. Here is sigma z, and here is sigma minus z. So these ligands will combine. This is ligand group orbital, and we have to combine it with metal. Then metal contain one s orbital, 3 p orbital, that is px, py, and pz, and 5 d orbitals, dx square minus y square, and dz square orbitals, that are eg, dxy, dyz, and dxz, that are t to g. Here we have taken the case of sigma donor ligands. So these dxy, dyz, and these xz orbitals will be non-bonding orbitals. Now, if we have to find the wave function of ligand group orbitals in case of s orbital, because s orbital lies in between and s orbitals is spherical in nature, so all the ligands approaching towards this will approach symmetrically. And so while calculating the wave function of ligand group orbitals in case of s orbital, we can calculate as the wave function in x direction and in opposite direction also, in y direction, and in z direction. We have added all the wave functions. So to normalize, there are here 6. So we will here this comes as root 6. So this root 6. So this is the wave function of ligand group orbital in case of s orbital. Similarly, we can also find in case of p orbital and in dx square minus y square orbital and in the d z square orbital. But in case of p orbital, the ligands will have head-to-head overlapping, whereas in a s orbital the ligands were symmetrically approaching. So if we draw the p orbital and the ligands are present, 6 ligands are present here in x, y, and z direction. And here is p orbital present. Here head-to-head overlapping occurs between this ligand and this ligand present in x direction. So to calculate the wave function in px direction, we can calculate as sigma x and minus sigma x and upon root 2. Similarly, if we take py and pz, similarly we will find for px, py, and pz.
Yes.
And if we have to find for d orbital, let dx square minus y square orbital. So if we draw the dx square minus y square orbital, now here the ligand is approaching in 6 directions. So here x and here ligand is approaching along x and y directions only. Because here ligands are approaching in x and y directions. So here while calculating wave function in dx square minus y square orbital, then
Yes, good.
we can
Yes. Yeah, today could you explain from your side? Next day we'll discuss is color and electronic spectra chapter. Yes, na? In coordination chemistry. Yes. Well explained in coordination chemistry.